On December 17, 1903, two bicycle mechanics from Dayton, Ohio, achieved what humanity had dreamed of for millennia. They conquered the skies. For 12 seconds, Orville Wright piloted a fragile contraption of wood, fabric, and wire across the windswept dunes of Kitty Hawk, North Carolina. That brief flight, covering just 120 feet, lasted less time than it takes to tie your shoelaces. Yet, in those 12 seconds, the Wright brothers didn't just lift off from the ground, they lifted civilization into a new age. What began as humanity's ancient fascination with birds soaring overhead has transformed into supersonic jets crossing oceans in hours, cargo planes carrying entire communities' worth of supplies, and spacecraft launching from airport runways. This remarkable journey from the Wright Flyer's tentative hop to today's aviation marvels and tomorrow's revolutionary aircraft designs reveals not just technological progress, but the relentless human drive to push beyond every perceived limitation. The story of airplane evolution begins long before the Wright brothers' historic flight. Throughout the 19th century, aviation pioneers laid crucial groundwork through experimentation with gliders, balloons, and theoretical aerodynamics. Sir George Cayley, often called the father of aerodynamics, identified the four forces of flight: lift, drag, thrust, and weight in the early 1800s. Otto Lilienthal's systematic glider experiments in Germany provided essential data about wing design and control, while Octave Chanut's engineering expertise helped bridge the gap between theory and practice. The Wright brothers succeeded where others failed, because they approached flight as an engineering problem requiring systematic solutions. Unlike many contemporaries who focused solely on achieving lift, Wilbur and Orville Wright recognized that controllability was paramount. They developed a three-axis control system, pitch, roll, and yaw, that remains fundamental to aircraft design today. Their meticulous wind tunnel testing, precise engineering, and methodical approach to problem-solving transformed aviation from dangerous stunts into reproducible science. Their 1903 Wright Flyer incorporated several innovations: a lightweight engine producing sufficient power-to-weight ratio, efficient propellers designed through mathematical analysis, and wing warping for lateral control. Most importantly, they understood that achieving sustained flight required mastering control, not just generating lift. Following the Wright brothers' breakthrough, aviation development accelerated with stunning speed. Within a decade, aircraft evolved from barely controllable curiosities to practical machines capable of military and civilian applications. European pioneers like Louis Blériot, who crossed the English Channel in 1909, and Alberto Santos Dumont, who achieved Europe's first powered flight, pushed aircraft design forward through competitive innovation. World War I served as a brutal catalyst for aviation advancement. Military necessity drove rapid improvements in engine power, aircraft speed, maneuverability, and reliability. Fighter aircraft evolved from reconnaissance platforms to sophisticated weapons systems, while bombers grew in size and payload capacity. The war years witnessed the emergence of legendary aircraft, like the Sopwith Camel, Fokker DR-1, and Spad S-13, the three each representing significant steps in aerodynamic understanding and manufacturing capability. Post-war aviation benefited enormously from wartime technological developments and trained pilots seeking peacetime applications for their skills. The 1920s became aviation's golden age, marked by record-breaking flights, air races, and growing commercial possibilities. Charles Lindbergh's solo transatlantic flight in 1927 captured global imagination and demonstrated aviation's potential for connecting distant continents. The transition from wooden fabric biplanes to all-metal monoplanes represented a fundamental shift in aircraft design philosophy. The Ford Trimotor and Boeing 247 pioneered reliable passenger service, while military aircraft like the Boeing B-17 and Douglas DC-3 established new standards for range, payload, and operational reliability. Engine technology progressed equally dramatically. Early aircraft struggled with underpowered, unreliable engines that severely limited performance and safety. The development of air-cooled radial engines and liquid-cooled inline engines provided the power necessary for larger, faster aircraft. Supercharging enabled high-altitude flight, while improved metallurgy and manufacturing techniques increased engine reliability and reduced maintenance requirements. Aerodynamic understanding advanced through systematic research and wind tunnel testing. The National Advisory Committee for Aeronautics, ACA, conducted groundbreaking research into wing design, drag reduction, and high-speed flight characteristics. These scientific approaches replaced trial-and-error methods with data-driven design principles. World War II compressed decades of potential aviation development into 6 intense years. Military requirements drove unprecedented innovation in every aspect of aircraft design. Fighters evolved from fabric-covered biplanes to sleek, high-speed interceptors capable of exceeding 400 miles per hour. Bombers grew from small tactical aircraft to massive strategic platforms like the Boeing B-29 Superfortress. The war's most revolutionary development was jet propulsion. Britain's Frank Whittle and Germany's Hans von Ohain independently developed practical jet engines, leading to aircraft like the Gloster Meteor and Messerschmitt Me 262. These early jets demonstrated the potential for dramatically higher speeds and altitudes, though reliability and fuel consumption remained significant challenges. Pilots marveled at the sheer acceleration and climb rates that were previously unimaginable in piston-driven aircraft. Yet these advancements came at a cost. Maintenance crews had to learn entirely new skill sets. Spare parts were in short supply, and fuel-hungry engines often limited range and endurance. Still, the promise of jet propulsion was undeniable. It marked the dawn of a new era in aviation. Radar technology further transformed aviation operations, enabling flight in all weather conditions and across vast distances with unprecedented precision. Pilots who once had to rely heavily on dead reckoning and visual navigation could now depend on ground-based and airborne radar systems to guide them safely through fog, storms, and darkness. This breakthrough not only enhanced military effectiveness during World War II, but also laid the foundation for modern air traffic control systems that keep millions of passengers safe each day. Alongside radar, pressurized cabins allowed aircraft to routinely operate at higher altitudes, where air is thinner and smoother, improving comfort while avoiding much of the turbulence and weather that plagued earlier flights. Instruments and autopilot systems also advanced rapidly, reducing pilot workload and making long-distance flights more feasible. Just as importantly, the war effort forced nations to refine mass production techniques, introducing new assembly line processes, standardized parts, and quality controls that made aircraft manufacturing faster, more efficient, and more cost-effective than ever before. Post-war commercial aviation quickly embraced jet technology with transformative results. The de Havilland Comet, despite its early setbacks, caused by structural failures from metal fatigue, remains a historic milestone as the world's first jet-powered passenger airliner. Its sleek design and smooth, quiet ride showed passengers what the future could hold, even if engineering lessons had to be painfully learned. Boeing 707 and the Douglas DC-8 soon followed, establishing jetliners as reliable, profitable systems that redefined global connectivity. Suddenly, the world seemed smaller. Journeys that once took days by ship or long hours on piston airliners could be completed in a fraction of the time. Business, tourism, and international relations all accelerated under this new reality. Jet engines offered numerous advantages over piston engines: higher speeds, smoother operation, greater reliability, and superior high-altitude performance. They could propel aircraft above weather systems, across oceans, and between continents with unmatched efficiency. However, they also brought new challenges. Early jets consumed far more fuel than piston aircraft, forcing airlines to adapt routes and fueling infrastructure. Longer takeoff runs demanded stronger runways, while specialized maintenance facilities and highly trained engineers became essential to keep the complex machines operating. Transition wasn't seamless, but it was unstoppable. Military aviation entered the supersonic era with fighters like the North American F-86 Sabre and the Soviet MiG-15, ushering in a new era of aerial combat during the Korean War. These aircraft demonstrated the advantages of speed and jet maneuverability, fundamentally changing tactics in the skies. Experimental aircraft soon pushed boundaries even further. Chuck Yeager's historic 1947 supersonic flight in the Bell X-1 proved that the so-called sound barrier could be broken, inspiring decades of high-speed flight research that continue to this day. From reconnaissance aircraft like the SR-71 Blackbird to cutting-edge hypersonic prototypes, each step forward expanded both technological limits and human imagination. Contemporary aviation represents the culmination of over a century's worth of relentless innovation. Modern airliners such as the Airbus A380 and Boeing 787 Dreamliner embody engineering sophistication that would have seemed like science fiction to early aviators. Lightweight composite materials reduce fuel burn while enhancing structural strength, allowing aircraft to fly farther and more efficiently than ever before. Fly-by-wire control systems replace traditional mechanical linkages with computer-assisted precision, increasing both safety and responsiveness. Turbofan engines, whisper quiet compared to early turbojets, deliver remarkable fuel economy while meeting increasingly strict environmental standards. Together, these technologies have made intercontinental travel faster, safer, and more affordable for millions around the globe. Military aviation has likewise evolved into highly specialized domains. Stealth aircraft such as the F-22 Raptor and B-2 Spirit can evade radar detection, altering the very nature of modern warfare. Unmanned aerial vehicles, once experimental, are now central to military strategy, conducting reconnaissance and even combat missions without risking pilot lives. Meanwhile, hypersonic research vehicles push the boundaries beyond Mach 5, exploring speeds that could redefine both defense capabilities and civilian transport. Each of these developments represents decades of research, testing, and risk-taking at the cutting edge of science and engineering. General aviation has undergone its own quiet revolution. Modern private aircraft now feature glass cockpits with digital displays, GPS navigation, and automated safety systems once reserved for airliners. These innovations make flying more accessible, reliable, and user-friendly than ever before. Beyond that, electric aircraft are beginning to emerge, promising quieter, cleaner, and more sustainable flight. Autonomous flight systems, long imagined in science fiction, are slowly becoming reality, potentially transforming how people think about both personal and commercial aviation. Looking toward aviation's future, revolutionary changes appear on the horizon. Electric and hybrid electric propulsion systems promise to reduce aviation's environmental impact, while enabling new aircraft configurations impossible with traditional engines. Urban air mobility vehicles may transform city transportation, while supersonic passenger aircraft could return to commercial service with improved efficiency and reduced sonic boom impact. Autonomous flight systems, artificial intelligence, and advanced materials continue pushing aviation's boundaries. Space planes that take off from conventional runways may soon make space travel routine, while hypersonic aircraft could reduce intercontinental travel times to mere hours. The evolution of the airplane from the Wright Brothers' 12-second flight to today's technological marvels demonstrates humanity's extraordinary capacity for innovation and progress. What began as a simple dream of flight has become a global industry that connects continents, enables commerce, and continues reaching toward ever more ambitious goals. As we stand at the threshold of aviation's next great transformation, one truth remains constant. The sky is never the limit. It's just the beginning. Thanks for joining us on this flight through aviation history. If you enjoyed soaring through the skies of knowledge with us today, don't forget to like, share, and subscribe to Epiven for more fascinating journeys through the world of innovation and discovery. Until next time, keep looking up.